Hi. I bet you think you know quite a bit about your own heartbeat. I bet you're aware of it beating, how fast it beats, but I also bet there are some details you don't know, and that's what I want to explain to you today, the sequence of events that makes up a heartbeat. We're going to talk about the cardiac cycle, and then in a related way about the Frank-Starling mechanism, which is related to heartbeats and the cardiac cycle and how it works in a mechanical perspective. So the cardiac cycle you can picture as consisting of a number of steps. Each one of them has an electrical component and a mechanical component. We'll talk more in detail about them as the semester goes on, and you'll hear a lot more about them when you take physiology. But we can break it down into these basic steps that you see in front of you here. The two important terms to keep track of are systole, which is contraction, and diastole, which is relaxation. Those are important terms that we're going to use all the time. This will come up in class, in the major project. You just got to learn them. Systole, contraction, diastole, relaxation. So the heart starts typically in mid or end diastole. It's the first picture we typically have. And then what happens first is the atria contract, and I'm sure you know already the atria are the two chambers in the top of the heart. That contraction takes place, a little bit of blood gets pumped into the ventricles, and then the ventricles contract. And that process also happens in multiple stages. And it's all controlled by valves. So the timing of the contraction and the valve opening and closing is critical to understanding the cardiac cycle. And after the atria have finished contracting, the ventricles begin to contract and very quickly close the one-way valves that would otherwise allow blood to flow back into the atria. So there are valves between both atria and both ventricles. The ventricles then contract, the valves shut immediately, and for a while there's a buildup of tension inside the ventricles, both the right and the left. And then at some point, they exceed the pressure on the other side of a second pair of valves, the valves that connect the right ventricle with the whole pulmonary circulation and the left ventricle with the systemic circulation. Now those valves eventually open, and when they do, blood then flows, is pushed out of the ventricles into their various circulatory subsystems. That contraction then continues, the heart gets smaller, and eventually the pressure starts to decrease. And it continues to decrease until the pressure outside those same two valves exceeds the pressure inside the ventricles, and the valves close again. And then the heart goes back into its relaxation phase. And again, there's lots of videos you can watch, lots of things online that will walk you through this in a very dynamic way, and I encourage you to go look at those. We're interested, for the purposes of our calculations, in actually developing a way of describing the cycle, describing the time events of the cycle in terms of the components we're most interested in this class, and that's pressure and volume. So we want to know what the time sequence is for the pressure in both chambers and the volume in both chambers. And for that, we have this amazing diagram called the Wiggers diagram, obviously invented by a physiologist named Wiggers. So this diagram, typically at the top or at the bottom, contains the ECG. That's the electrical signal that you'd measure on the surface of the body during the cardiac cycle. And then below that are these mechanical factors. And they can be pressure over volume over pressure. That's not important. What's important is there are two pressure tracings that you see in front of you, one in red, one in blue. One of them describes the left ventricular pressure. One of them describes the left atrial pressure. And there's even one at the top, if you look carefully, that describes the aortic pressure. And those are the pressures of the various elements of our system. You see the left atrial pressure is very low, doesn't contract as strongly as the ventricles do. That's where the bigger pressure fluctuation occurs. And the aorta, which is the biggest vessel that the blood flows into from the left side of the heart, the pressure there is much smoother than in the left ventricle. There's a phase when it's identical to the pressure in the left ventricle, and that tells you what? It tells you that they're connected. So when the left ventricle is connected to the aorta, That happens when the aortic valve opens. And at that point, there's blood flowing from the left ventricle into the aorta. They're connected. They have the same pressure. It's the nature of pressure. So at that phase, they have the same pressure, but otherwise they don't. And the aortic pressure tends to be smoother, fluctuates less dramatically than the left ventricular pressure. And that's what you see if you compare this blue curve at the top and the red curve just below it. On the right side of this diagram, you see the same curves, but for the right circulation, so the right ventricle. And not the aorta, but the pulmonary artery. This is where the blood goes when it leaves the right ventricle and heads off to the pulmonary circulation, the circulation that supports the lungs, the pulmonary system. But otherwise we see similar shape traces, just dramatically smaller pressures. And that's a key characteristic or characteristic difference between the left and the right side of the heart, we call it, the left and the right ventricle explicitly. Now down below that you see the volume and the volume change over time. And there you see again on the left side, you see the volume in the left ventricle, on the right side you see the pressure, the volume in the right ventricle. And you can see there they go through similar shapes and similar patterns. And that shouldn't be a terrible surprise. We'll think about this, we'll come back to this maybe later, as to why the pressure curves are so different, but the volume curves are very similar in shape between the left and the right side of the heart. That has to do with, guess what? A conservation law. It's physics after all. So that's the Wigger's diagram that describes the time sequence of pressure, volume in the left side and the right side in the ventricles and the atria. Now we can highlight a couple of curves in these multiple time curves. One of them is the curve for the left ventricle, and the other is the volume for the left ventricle. You see them highlighted here in orange. When we highlight those two curves and then plot one against the other, so we plot one against the other. This is a parametric curve, fundamentally, and we use these a lot in engineering. The downside of a parametric curve is that the time goes away explicitly. We lose that time axis in our plot, but we gain something else. And the result here is something we call the pressure-volume loop, or the PV loop. And what you see here is volume along the x-axis and pressure along the y-axis. And this tells us the whole sequence of pressures and volumes as we go through a cycle of the heartbeat. And you see two different curves there. The taller one, the one with the higher pressures, of course, is for the left ventricle. The smaller one is for the right ventricle. You also see something interesting related to what I mentioned previously, that the width of these curves is the same. So what is the width of this curve? This is an important factor when we think about it. That's the difference between the maximum volume and the minimum volume. When you think of what the heart does, it fills and then it contracts, and it fills and then it contracts. And the difference between the minimum volume and the maximum volume, that's equal to something we call the stroke volume, another term you'll have to get used to. And stroke volume multiplied by heart rate is cardiac output. And these are all quantities that we'll use in the major project in this class and throughout your lives. So we have a curve or a line that makes the stroke volume. Now these pressure volume loops are useful in and of themselves. They're another graphical form of capturing the behavior and really the performance of the heart as a mechanical pump, as a contracting mechanical pump. And we can see pressure, we can see volume. It turns out the area within that curve, we can show mathematically, is equal to the work that the heart actually carries out. That volume there represents the behavior, the performance of the heart. And when patients are ill, when they get into situations of what are called heart failure, then that shape will reduce in one direction or the other. And we'll see in a second how certain things like exercise can cause that loop to change in other ways, good ways, not ways that are connected with a pathology. So that's the cardiac cycle. That's the parts we really have to know about because we'll be using this again and again. Now I want to switch gears quite dramatically and think about something called the Frank-Starling mechanism. Guess what? It was invented by two physiologists, one named Frank, one named Starling. One was German, one was British. So the idea here is to try and explain a behavior that we can observe in people, all of us, who are exercising. So one thing we start is we look at this schematic diagram here, which represents, believe it or not, the heart and the cardiovascular system. You can picture it as systemic circulation, doesn't really matter. So picture it as the left ventricle. I said before that cardiac output is equal to stroke volume, the width of that PV curve, times the heart rate. And that tells us how much blood the heart pushes out, that's the cardiac output, per unit time. Because heart rate is per unit time, stroke volume is a volume, and so we have volume per unit time. That's the cardiac output. Now, the heart itself is a pump that beats regularly. That's the little piston you see going up and down. And there are those valves we talked about. You see those there schematically as well. And then we see this pulsatile output of the heart. And we'll learn a little bit later how that pulsatile output gets a little bit smoothed by the compliant vessels and all that jazz. But the main thing to note here is we have a pulsatile cardiac output, but we can measure that on a stroke by stroke or a cardiac cycle by cycle, beat by beat basis, and we can actually put numbers to that. And we happen to know by measuring people that 55 milliliters, something in that range, 50 to 60 milliliters, is a pretty good number for a stroke volume for a young, healthy adult. Numbers differ slightly from men and women, of course, but that's a reasonable ballpark number. So we have a stroke volume, pretty small when you think about it. 55 milliliters is not that much, but we have a heart rate of 60 beats per minute. So the question is, what's the cardiac output? So take a second, see if you can write down or calculate, it's a simple calculation, you can do it by hand, what is the cardiac output given these two parameters? So you can do that, and it turns out you get a multiplication, and you get a number like 3.3 liters per minute. So think 3 to 5, something in that sort of range. That's the heart rate, or excuse me, that's the cardiac output at rest of a, let's call them normal person, whatever that means. So a typical young, healthy adult. That's the situation at rest. Now what happens during exercise? Many fantastic things happen during exercise that allow us to exercise. We're going to focus on the heart itself and how the heart changes. So what changes then? It turns out that when athletes are performing at their highest level, they achieve incredible, to my mind, cardiac outputs. They have a cardiac output at maximum exercise among the elite athletes that is something like 35 liters per minute. So we've gone from 3.3 or 3.5, if you want to have a nice round number, up to 35 liters per minute of cardiac output. That's a tenfold increase. And you think, well, how can that be? Tenfold increase. That's amazing. I mean, there's not many things we can do that get 10 times better. No matter how much we train or whatever, you know. So that's an amazing situation, and there's lots to say about that we don't have time for. But now we have cardiac output, and what happens typically with exercise, as you know, is your heart rate goes up. And 200, that's again, not unusual, pretty normal upper heart rate, truly upper heart rate for an elite athlete. It's not, not unreasonable. And some of you may have maximum heart rates in this range. It varies a lot with genetics and age and all sorts of other things, but 200 is not a bad number. Now we have cardiac output and we have heart rate, and those are real numbers. So now we can ask the other question, what would the stroke volume be? Does the stroke volume change with exercise? Really reasonable and sensible, curious question to ask, actually. Does the heart know we're exercising and push more blood out with every stroke of its contraction? That's what stroke volume is. It turns out if you do the very simple math here, it's just a quotient, you'll get a number that is substantially bigger. You'll get, in this case, 175 milliliters, which is a lot bigger than 55. So it's substantially bigger. Now, what is it that brings about this change in exercise? How does the body actually do that? Well, it turns out that, of course, not surprisingly, the brain plays a role. The brain controls a lot of our functions. It fine-tunes things. It does things like increase heart rate, lots of other things that you'll learn about for a long time to come. And some of them we will talk about in this class. But we're going to talk about something else because the brain doesn't fully explain what we see in the heart. In fact, we can do experiments where we sever the ties between the brain and the heart will keep beating. We can remove a heart in an animal, let's say. We can remove that heart from the animal, from a mouse, a rat, a guinea pig, whatever animal you can imagine. You can remove that heart and it will keep beating. It has its own intrinsic, what we call a pacemaker. It's a whole other interesting story. But the point is that the heart rate is in part controlled by the brain, but there's another part to it that we can see in patients who are the perfect test subjects for this type of question. As in, the question is, what does the heart do in exercise when the brain is not attached? Now, what would be the situation that you can think of that would describe such a case of a patient with a heart that's beating, they're alive, they're awake, they're running, but has no brain attached to that heart in order to control it? Can you think of that? We'll talk about that in the discussion section this week, and you can see if you can come up with that idea in the meantime. It's something you know about for sure. But the point is that it's possible to do this experiment, and if we do, we see PV loops, pressure volume loops, like you see below there, that get wider. And remember, the width of the PV loop gives us a measurement of the stroke volume, how much blood leaves the heart with every contraction, because you have the full end diastolic volume, and then you have the end systolic volume when that PV loop gets smaller. Or not the PV loop gets smaller, but the PV loop travels around from the far right to the far left. And that distance is the stroke volume. So how does that happen? That's what we're trying to explain, because that doesn't make any sense. Nothing most of you have learned by now would give you any reason why this would happen. Now, to explain this, we're going to do something that we do a lot in physiology, and I would say a lot in biomedical engineering, is we try and reduce the system and understand how its components function and respond. So we're going to take that heart and think about it as a whole bunch of muscles packed together into chambers. And we're going to look at how a muscle behaves to an interesting experiment that we're going to perform. So here's our experiment. So we have a muscle, that's the orange thing there. It's a little muscle bundle, you can picture it lots of different ways. And then we have a plate connected to the bottom of it, and it's connected at the top as well. So that muscle bundle is suspended and held in place between these two plates. And the plates are rigidly held in place. The left picture you see there is the muscle at rest. Now we're going to stimulate that muscle. You can do this with electric shock. That's the simplest thing to do in an experiment. You shock it a little bit, that muscle contracts. Because the plates are fixed, it can't actually shorten. All it can do is get thicker. So the muscles get thicker. This is an isometric contraction. You can try this at home. Try grabbing your door and see if you can squeeze it together. You can't. The door will hold up to you unless you have a really bad door. But you'll see your muscles in your arms that you use for that and your pectoral muscles in the chest, they will get thicker. They will stand out. That's this same effect that you're seeing here. Now, if we were to measure that, if we were to measure the tension developed, so how much pull there is on that plate at the bottom, and as we stimulate that muscle, we'd see what's called a twitch. That's that signal you see at the bottom. And we have a resting tension, and then we have on top of that a stimulated twitch. And now the question is, what will happen if I move that lower plate? In fact, I'm going to move it down a little bit. So what would happen? I'm going to stretch that muscle a little bit more, and then I'm going to do the same thing. Stimulate it with the same shock strength, and watch what happens. Any guesses what's going to happen? We'll see. What happens is that muscle, of course, doesn't get any shorter because it can't, but it starts longer because it's been pre-tensioned. It's been stretched a little bit before it contracts. That's the scenario. Any guesses now what's going to happen? All right, what happens is that we get an increased resting tension. That's not surprising. But what is surprising is the twitch tension goes up. If you look at the magnitude of that twitch, it's higher now than it was in that original state. And that is surprising. That's a surprising finding that I would say you probably wouldn't anticipate unless you've done this experiment yourself or read about it. And what if we continue stretching that plate? We can do that too. We can continue pulling on the plate, stretches the muscle even more at rest, stimulate even more. What do we get then? Oh my goodness, the twitch goes down. The pretension goes up. That resting tension is elevated because we're stretching that much more, but the actual strength of the contraction, the tension developed by the contraction, is actually reduced. And if we pick more points along this axis of stretch, we did 3 steps here, we could do 20 steps or whatever steps we needed, we could then draw a curve that is a function of the pretension and measures the twitch tension, the height of that little spike. And we can plot those. And that's what we do to get a curve that looks something like this, where we have time across the x-axis, and time is short in the sense that every one of those little twitches is quite short, literally just, tens of milliseconds maybe in length. And then the longer term time is, let's say we did this in sequence where we pull down the plate every time. Each one of these traces is after pulling the plate down a little bit more in a obviously carefully measured way. And we'd see a curve that looks like this. And we'd see the lower curve going up because pre-tension is increasing, but we'd see the upper curve going up even more dramatically. The upper curve gets very large because we have a larger twitch strength at certain pre-tensions. So now if you sort of absorb what that means and think, okay, the strength of the muscle contraction is a function of how much I stretch it before I contract it. Now make the big leap. This is not simple, but I think you can do it. Make the big leap into thinking about how the heart works, right? So we have a heart, we fill it with blood. Blood comes back from the lungs or comes back from the systemic circulation back into one of the ventricles. And that blood returning to the heart stretches it. For example, imagine exercising, where we have a lot more blood needed to support a lot more muscle, doing a lot more work. So that blood would return. We've seen that the cardiac output is enormously larger at maximum exercise, 10 times larger. That means there's more blood coming back into the heart for every heartbeat. And that increased blood flow causes increased stretching, pre-tensioning of that ventricle. And so when the heart beats then, it's beating with a larger starting tension. And what's it going to do? Just like these muscles, it's going to contract more strongly. And so we can draw another curve, this time based on the filling pressure into the chamber, and then the stroke volume of that chamber. And we get a curve that looks like this. And I added in these axes here to make it clear that the x-axis is similar to our passive rest tension, which we had in the previous diagram, and the y-axis here corresponds to the twitch tension at the single muscle bundle level. But of course, when you put it together in a whole heart, you get the stroke volume, and the stroke volume goes up. And that is the Frank-Starling mechanism. The more blood that returns to the heart, the harder or the more forcefully the heart contracts, and the result is an increase in stroke volume. Now, at the macro scale, what this allows the heart to do is be what we call a compliant, not in the sense of stretch, but a compliant pump, in the sense that no matter how much blood comes back to a normal heart, that heart can cope with that increased returning blood by beating more forcefully. It may also beat more rapidly. That's where the brain comes in. There are signals going back and forth in a normal heart and normal brain that will tell the brain something's going on, there's more blood flowing. The brain will then tell the heart, okay, you got to beat a bit faster. There are other mechanisms, turns out, that also have the same effect. So heart rate certainly does go up, but contractility or shortening of those muscles also goes up, stroke volume goes up, and the result is an increase in cardiac output to reach some of that tenfold increase that we described for exercise over resting hearts. Another way to picture this, and this is another immediate use of the pressure volume loop, is we can see there's one pressure volume loop there. Here I labeled it with left ventricular stroke volume. That one that starts in the left and goes most of the way across, that's the resting one, but it can increase even further. It can move further to the right. And this is a schematic, so don't worry about the scale here too much, but it can go further to the right and we can get more filling, and the net result will be a bigger distance between the end diastolic volume and the initial, it's really end diastolic volume here and end systolic volume over here. So the end diastolic volume is the maximum filling volume. The end systolic volume is the minimum volume after contraction. And that distance, which you see in the pressure volume loop, gets larger. And that tells us that the stroke volume increases. And that explains one of the effects, one of the many effects that exercise has on our hearts. Now, in the interest of full disclosure, the extent of the Frank-Starling mechanism and the way it works and some of the other control features of it are still the topic of research, even though this has been a mechanism that's been taught to students for many, many years, for decades. It's a well-known mechanism in lots of circles, but is not, as with a lot of physiology, completely without controversy. But I'll leave that controversy to a later point in your studies. At this point, what you have to know is that we have a cardiac cycle. It has volumes and pressures, which we will care about a lot because that's what our major project is about. And we have a mechanism that allows the heart to beat more forcefully whenever it's filled more fully, by whatever mechanism. That's the macroscopic behavior we care about, and that's the one that we'll be building into our models of the cardiovascular system. Thanks a lot for your attention. Hope that made some sense, and I'll look forward to talking to you later in the week about some of these questions that I brought up during this lecture. Thanks so much. Bye-bye.